Welcome everyone to the ICTS monthly colloquium. It's a great pleasure to have Professor Mahendra Verma from IIT Kanpur give our colloquium this month. Professor Mahendra Verma is we all know he's a excellent researcher in the area of turbulence, magnetohydrodynamics, buoyancy-driven flows, and non-equilibrium stat-mech. He's also received several awards and fellowships, the Swarna Jayanti in 2006, an INSA Teachers Award in 2016, J.C. Bose Fellowship in 2023, and also the Sanjay Mittal Chair at IIT Kanpur from 2019 to 2022. He's also a member of several academies in India. He's written several books on computing and fluid dynamics. You'll see maybe several simulations. His group page also has access to the codes, so you should definitely check out the publicly available code that enables this kind of calculations. And with that, I'll hand it over to Professor Verma to give his talk.
Thanks, Vishal. Good evening, and thanks to Vishal and Rajesh to make it possible that I'm here. So I really like this place, so thanks for the invitation. So this is the title, is famous problem. So you can see the scope of the problem by number of books written on it, number of videos, Nobel laureates have given talk on this. Also the movies, like I don't know, you are aware of this?
Back to the Future.
Yes. But, sorry, I kind of. Yeah, so it's a Back to the Future. There are three-part series going back in time. There's a time machine book written by Wells. So, but I will keep it semi-technical. In fact, it turns out, according to me, if you look at from different perspective, the problem is easily solved. I mean, this it's not a problem anymore. If you see from macroscopic point of view and from multiscale perspective. Now, these are several papers which I wrote recently. So let's get to the problem itself. So this is a lot of theory institute, no? So I had to start with the real theory. So symmetries, no? So we know there's symmetries, continuous symmetries and discrete symmetries. And these symmetries, this is for the pointer, no? This is for the yeah. So there are three continuous symmetries which are respected for isolated system. I just do want to make it clear that if I take my experiment in free space and I do it in region 1 or region 2, it doesn't matter. Laws of physics remain unchanged on space translation, space rotation, and time translation. And they lead to conservation laws, respectively. Now, very clearly, if I do the experiment on Earth, suppose with involving magnetic field, and that experiment I have to be very clear. If I don't isolate the magnetic field, then Earth's magnetic field will interfere with it. So if I don't make it isolated or don't isolate it enough, then the symmetry is not respected anymore. Okay, so that is what happens for arrow of time. That's what I want to just say, that isolated system is an important assumption for a lot of these symmetries. Now, of course, we are going to talk about this, but I'm going to touch upon this as well a little bit. So there are three discrete symmetries: charge, parity, and time reversal. Charge conjugation is that if in isolated system, I replace particle by antiparticle and do the experiment, I'll get the same result. Of course, something is, so it just had to be for particle-antiparticle symmetry. It was supposedly should have worked, but it doesn't. There are some violation, minor violation. Same with mirror. So I'm going to show an experiment which violated it in particle physics and also in real life. Okay, so I'm just going to, and this time I'm going to use it for time reversal. Okay, and time reversal is, so parity is that if I do an experiment with components which are all the left-handed systems are to be replaced by right-handed systems. And then the experiment should give same result irrespective of the handedness. And time reversal is, which I'm going to, well, let's keep it for 2 more slides later. So if I reverse the system in time or make the time go backward, then what happens, okay? So let's look at mirror symmetry, okay? This is something which we see all the time. So these are in fundamental. So we have fundamental experiments. Most experiments respect the symmetries, but some symmetries are broken at fundamental level itself. So parity is one such. This was experiment by C.S. Wu. So these are real experiment. So cobalt nucleus emits beta particles, electron, but it turns out the spin of the cobalt nucleus and the velocity of the beta particle or electron, they are anti-aligned. So V dot S is less than 0. Now parity is also connected with mirror. In fact, they are same. Mirror plus rotation leads to parity. So R going to minus R is connected with the mirror. Okay. So in mirror, we have velocity will switch sign. You can see that something going to the left will go to the right in the mirror, but spin does not. So in the mirror, we get V dot S to be positive. So you see that in life, we have V dot S less than 0, but in mirror, V dot S is greater than 0, so it is violated. So this experiment, by seeing it, we know that this is not a real experiment. Okay, so mirror symmetry is violated from this experiment. But now let's look at real life. So some nice pictures. This is, if you visited IIT Kanpur, you'll see this in 2 seasons, autumn and spring. So Amalta's fruit tree. Now, if you look at the shells, you will find them plenty right now. It is twisted. Now, these breaks the symmetry. No? This is helical. This is handed. It is twisted. So, what is breaking the symmetry? Is it coming from weak nuclear interaction? No, it is not weak nuclear interaction. It is environment which is causing it to twist. So, the left side and right side of this shell, it is not a leaf actually, it is fruit shell. They have different moisture levels and they dry at a different rate. So wood, the wood bends. Similarly, this is bending too. So it is connected to environment. It is not an isolated system and parity is breaking everywhere, including my heart is in one side of the body. So it's evolved like that, but it is broken at some level by the environment. Which one? Heredity. So heredity also coming from parents, in some sense the environment, you can call that way. Or it is connected with, it's not isolated, it is coming from the neighborhood and environment. But this one definitely one can say that environment is playing a big role. No, it is drying up. Without sun, you won't get this kind of bending. So well, this is where I think I'm trying to say that we can't look at the system like you can simulate the atmosphere starting with molecules or from quarks. Well, we can't simulate from quarks, but it's best to simulate from atmosphere point of view only, from fluid velocity. So it depends on which level we want to look at it. For me, it's practical to look at it from this moisture level, and that suffices. So, and for me, I can now conjecture, or I can show that arrow of time can be solved by this perspective. That's why I said multi-scale perspective. Now, of course, perspective is personal, subjective. So I'm just saying that this perspective is also an interesting perspective. I will not fight it. Of course, some of it can be said, well, I can explain it from microscopic perspective, it's fine. But sometimes practical, we can do it this way, thinking on that. Okay, now let's look at time reversal, which is the topic of the talk. Now the statement is pretty simple. So I will go with Newton's law, okay? So we can also do it for Schrodinger equation. So this equation is second order in time, but force is not dependent on time. So I just want to make it clear that it's only R. Gravity, electrodynamics, Coulomb interactions, they are not dependent on time. So if force is symmetric to T to minus T, then this equation is symmetric. So now if we have solution R of T for this particle, then if I reverse the trajectory, so the example is here. So in vacuum, I have projectile going from A to B. Okay, so it's a parabola. Now, if I reverse the velocity at B, then it will follow the exactly same trajectory. This is a simple example, but even for complicated trajectories, a reverse trajectory will be a solution. It's a valid solution. Or we can say that if I play the movie backward, so I play the movie backward, then we cannot differentiate. We can't say that this is a fake movie. Okay, so that's a test for time reversal symmetry. That is what is quoted as time reversal symmetry, which works for particles, especially for under gravity, projectile, or the pendulum in vacuum, will pendulum moving forward in time, or reverse pendulum will show the same. I mean, you can't differentiate. I can't say this is a fake movie. But we'll see in real life. Well, there's another experiment. This is a pretty nice experiment I dug out from internet. So one may say in particle physics, is the time reversal symmetry broken? And all this won the Nobel Prize, except Madame Wu. She unfortunately did not get the prize. But this one won the Nobel Prize. Krunin, I think, right? Krunin got this prize. So we have this meson, which is B and bottom quark and D quark. So these are meson. So this transitions to this. I'm not expert of this, so my knowledge is very superficial. So this meson gets there in time t1. This time t1. Then it goes back to the original meson in time t2. This is not symmetric. So this time is not same as this time. If you play the movie backward, then what's going to happen? Then this guy will go there, then go there. So this is shown here. So this is connected here. It goes from here, there, and there. So the law is that it goes from this B bar D to B D bar, longer time. But in the reverse movie, B bar D to B D bar is shorter time. So we can say that this is fake movie. So that means time reversal symmetry is broken in this experiment. And this is a very important fundamental experiment. Now, we look at in macroscopic world. So this Rajesh just cleared that particle decay. I was asking a question, neutron decays to proton. To me, it looks like I can't reverse it. But it is similar to what happens. Well, so this is a question we'll keep in mind. We'll push it for later. Okay. Now let's look at the real world. That's my domain. So fundamental laws are symmetric in T-symmetry, but what about macroscopic world? We see it broken all the time. I'm going from here to there, So every time. So this is a gas confined in a left side of the wall, left side of the box. It expands to the whole box. So why so? Now this looks, in fact, a lot of people say it's a big problem. But if you look at it from macroscopic perspective, which I'm going to show you, well, first of all, Boseman spent his lifetime, Boseman-Gibbs, and they say entropy is the direction of increasing in entropy, because entropy never decreases, will be a pointer for time arrow of time. So there's this very nice experiment, in fact, to test the entropy increase or thermalization. Fermi Pasta Ulam, they did computer simulation. And the simulator who wrote the code is I can't pronounce it, Shungu, okay? And now this is a 1D chain of springs, but they're nonlinear springs. So the coupling between the two particles, the spring is nonlinear. That means minus kx plus x cubed, that kind of interaction. Now what happens to the spring? Now, even now there is some work going on to simulate it, typically simulate it. Nonlinear systems, we normally don't have exact solutions, except some isolated ones. So this one, for weak interaction, so the x cubed term is weak compared to kx, then it's quasi-periodic for weak nonlinearity. But if interaction is made stronger, it's random and thermalized. Okay, so that is a claim in some paper dispute it. I think it's still an open problem, but and there are some experts in the audience. But let's take that as a kind of a generic scenario. So this system, if I make it nonlinear, large number of springs, large number of particles, then the system is going towards randomness. Now, the question is, will it come back to the original configuration. Now, if you have large enough systems, then Poincaré recurrence theorem is invoked by, in fact, which is true. But the time scale that it can reverse back to the original configuration is pretty large. So typically, it's assumed that in a lot of condensed matter systems, it will basically thermalize and it won't go back to the original configuration in finite time or realizable time. So, sensitivity initial condition also plays a role here. This final state depends on what initial condition I start. So now we have two things from just simple discussion which I did so far. We have T-symmetry, time-reduced symmetry. We say that I should be able to go back to original distribution, except I need to reverse the velocity fields. Okay, sometimes it may be very difficult. I'm going to go to those cases a bit later, but this is I should be able to grow younger. That's the claim. If I do it proper transformation, that is T-symmetry. But this one says, well, is going to go typically to randomness, and we have very nice condition, but any change in initial condition will make it thermal. Now, macroscopic world essentially goes towards the direction, except some cases it doesn't, but it is not going to the original configuration. Okay? So this is in macroscopic world, we don't get it often, which is obvious, we can see it all around us. So what are the mechanisms? So I'm going to just show the mechanisms which I'm going to deal with right now. When I'm going to expand some of them during this talk. So entropy is like more than 100 years of research. So this is one invoked mechanism. But I'm going to show you that some systems, entropy is not well defined. Okay, I'm going to explain why it is not well defined. I hope I can convince you that entropy is not defined for some systems. So that's where we need to say, maybe you can use energy transfers. In turbulence is one such example, where entropy is not well defined. Here, the energy transfer from large scale to small scale. So the energy goes from large scale to small scale, is one directional, it breaks the time symmetry. Other thing is pretty obvious, is open systems like combustion. Combustion is breaking the symmetry because something explodes, it doesn't go back. And during explosion, it generates photons, phonons, sound waves. So these are pretty much irreversible processes. And last one is asymmetric objects. In fact, this example is pretty obvious. The spherical balls, under collision, we can go forward and go, we can play the movie backward. We cannot typically, this under this ballistic collision, we can't differentiate the forward movie and backward movie. But if projectile like rocket is going one direction, reverse the projectile motion, I can differentiate the backward movie. So extended object, which is asymmetric, can be differentiated. And almost all the time, we find in nature objects are asymmetric. So that experiment, which is idealized stuff, doesn't happen in real life. And molecular collision. In fact, this is not, this is there in chemistry all the time. And this can break the symmetry too. So let's get into one by one, and I'll just keep the discussion simple. So is entropy defined for all systems? So I'm going to show you some examples. So we have, this is a formula by Boltzmann, great, it works very well for ideal gas. So this is ideal gas with n particles, volume V, temperature T, and we define entropy. There's a formula with log V and log and so on. But I'm going to make some change. I will heat the bottom and cool the top, but this temperature difference is not a lot. So the heat will get transported by conduction. Okay, but T1 and T2, the temperature difference is not a lot. So I can still apply Boltzmann entropy. This is near equilibrium. So somebody may say, well, you can't really apply, but let's apply. Okay, people do it. This is what is done. So we apply Boltzmann formula and we get an entropy formula. Okay, Kb log of Z. Now let's change the experiment a bit. So I'm near the critical temperature, which may not be again large, maybe 20 degrees, 30 degrees. And now just above the onset, so there's a critical temperature, and above the onset we get nice rolls. So this is a convection roll. Now I'll just ask the simple question. This was kind of asked by Prigogine many years back. So what about entropy of the system? Is it, so I look, the temperature difference with the temperature, mean temperature of this gas and this gas is nearly the same. Not a lot of difference, maybe few degrees. So Bose-Einstein entropy should not give a very different number. It should be off by maybe 1%. But here I do see this nice structure, flow structure. So my eye says it's more ordered. But Bose-Einstein formula is saying, no, it is not more ordered. So how do I explain this order? So let's invoke a formula which is known in electrical engineering. Electrical engineers have been using this formula for signal processing. So given a signal, how do you say it is more ordered or less ordered? So this is in a similar spirit. I got to know it a bit later. So we do Fourier transform of this, and then I can define, I can get energy, which is mod UK squared, velocity mod squared, that is energy in a Fourier mode K, divided by total energy, and I call it P of K. Okay, I need a formula, okay, so you can interpret it as a probability if you like. And then I'll use minus Pk log Pk, and that is my hydrodynamic entropy. Deepak objected, don't use the word entropy for it, but okay, I can call it some other name. Okay, so it's a measure of order, and low entropy will be less SH, high order will be less SH, and disorder will be more SH. And we did compute it for Euler flow. I'm going to show the Euler next slide. Euler is a very nice example, which is not so unreal. Superfluids are like Euler in some first order sense. So we have start with this ordered state. It is a cross section of a 3D flow. So we have structures, this is structures. And if I evolve from here, then I go there, which is randomized. Euler flow 3D does become thermalized. It is as random as the thermodynamic gas. And so what about the order? This looks more ordered than that. But according to the Bose-Einstein formula, there is no heat production because viscosity is 0. If there is no heat production, the entropy cannot change. Delta S is delta Q by T. Delta Q is 0, no heat production, so entropy cannot change. So it's standard textbook stuff, yes.
So I'm going to ask a very basic question.
Yeah.
I would have thought that to define entropy, first we need a notion of coarse graining. And let's say we do have a notion of coarse graining where we decide we have some set of macroscopic observables OI. Yeah. Then I would have used the Jane's S maximization prescription to define an entropy. I would have said, look for the density matrix that gives you the correct expectation values for those observables, and then try and maximize the von Neumann entropy with respect to those constraints. Why is that not a satisfactory definition of entropy in all cases, including in the case that you mentioned? Maybe I'm missing something basic, but I would have thought it should be a good definition.
Okay, I mean, I'm not dug into it, these formulas, I'm sorry, I really don't know, but it could be equivalent. But my claim right now for the talk is that Bose-Einstein entropy is not sufficient to give the order. Okay.
So I would just define it as follows. We could do it in a distribution in phase space if you like, but or in the quantum mechanical system might be easier to understand. We just look at the density matrix and we ask what is the density matrix that is consistent with the velocity flows that we observe.
Okay.
And then we try to ask in that space of all density matrices, how do you maximize the von Neumann entropy, which is the trace of rho log rho. Now, clearly the set of density matrices where you've put this constraint that there's a flow, that will give you a much smaller, value of this maximum.
So, I don't object to that when we try it, but there's several ways to look at a system. So this formula is pretty straightforward, no? So simple solution is always, for me, I understand it and I use it. And I'm going to show you that this gives a very meaningful measure for Euler flow.
Think of this as some version of density in phase space, just as a phase space density, and then think of this as a standard Shannon entropy, maybe in the classical case, or is that?
Actually, I can tell you, there's a paper which is here. This is multiscale. It is capturing, Fourier modes are capturing order at different scales. So for Euler spins, in fact, we just discussed with Rajesh, we can compute Shannon entropy with which Euler spin. That gives us proportional to n. Entropy is proportional to n. This one is log n. So it's non-extensive. it is not, it's not the same. It's quite different. It's
I
non-extensive, yes.
I think what you are considering is like a more finer coarse graining description than just in VT.
By the way, it's coarse grained at different levels.
Yes.
It is
So that's why
multi-scale
you
level.
see these structures.
It's a
This is also
multi-scale.
there in the description. That's why you have to define a entropy in that description, not in the largest coarse grained description, which is just in
Actually,
VT.
there's not only one level. I'm looking at order at different levels, and it is capturing
I
that.
think what he's saying is that if you coarse grain to say that the only degree of freedom was the temperature, then at that coarse graining, it might be the case that these two have the same entropy.
But
But you should have a finer coarse graining to see the difference between them, and it makes sense
Look,
to have a finer coarse
Look,
graining.
I think here there's no temperature definition in Euler flow. There is a temperature here, but there's no temperature for Euler.
You had a very coarse graining, you might
But
not see.
why should I use that definition? Why can't I use another definition? Electrical engineers use the definition, and I'm using the definition. Okay, so yeah, so let me use the definition, and let's carry on the story in finite time, and we can discuss it. I'm open to it, and I hope this will lead to some more investigation of computing Farnham entropy for this. I'm open to it, but this works reasonably well, and let's look for independent ways to look at it. Surely, I think it's a rich problem. Now in 2D, this is another interesting problem. So we start with some initial conditions, 3 initial conditions, and it turns out this system does not thermalize. That's my, we had a lot of difficulty getting referees convinced, but we ran it for long times. 4300 degree turnover time is the longest for 2D systems, and it does get more ordered with time. So we looked at the same formula, that SH, and these are for 3 different runs. Entropy is decreasing with time, that SH. It is not thermodynamic entropy, but this is getting more ordered in the hydrodynamic sense. Okay? So this is not thermalized, and there are systems like people are talking about time crystal now. So systems need not thermalize, and this is one interesting example where it is not in thermalizing. And this SH is a very good formula, because how do I quantify is getting more ordered? How is it thermalizing or not thermalizing? And it is work. Yeah.
Take one component hard sphere gas.
Okay.
At very high pattern fraction.
Okay.
Let it go. Add pattern fractions in its equilibrium state in the crystal.
Right.
It will get progressively more ordered in time, but its entropy will be increasing in time.
Yes, I am aware of this rods, different. But here, so this one way, so I'm not getting deeper into this, but here there's an energy flux, which is another measure for equilibrium. So energy flux is non-zero. There's a detailed balance is broken. So that's another perspective from which saying is non-equilibrium. And it is not reaching a state, which happens in 3D, where energy transfer is 0. But this one is not, energy transfer is not 0. So there are several ways we arrived at the conclusion that is not thermalizing.
There's a non-Hamilton in your case, that's what makes it a crystal.
In that particular case, it's just hard spheres doing nothing but this. You can implement it by any other actual.
There's no long distance interaction.
Just name out this. Hard spheres that low pattern fraction are fluid and high pattern fraction they are resistant. Or you saw it low pattern fraction are fluid, isotropic fluid, and high pattern fraction they are aligned.
Okay, so let me get there first.
That's coming from phase. Okay, no, but yeah, I mean phase, yeah.
All right, so let's look at turbulence. So as I said, this here, if entropy is, I in fact don't know, I don't want to even go to SH, hydrodynamic entropy, but let's try to see whether we can define arrow of time for hydrodynamic turbulence, the fluid turbulence. Okay, like I said, Euler equation is not, Boltzmann is not working. So how do I define arrow of time for such problems? Now we can use energy transfers, which makes it non-equilibrium, and that also gives us arrow of time. So here in such systems, typically, this is a generic prescription, not every system, but many of the large-scale non-equilibrium systems are driven at large scales. They dissipate at small scales, and there is a cascade of energy. it doesn't happen in 2D, but 3D it does happen. That energy goes from large scale, large vortex to a small scale. It just flows. And here at small scale is local equilibrium, local near equilibrium. So that is the direction it goes, and I can use that for define arrow of time. Now, to make it more mathematical, if you like, so this is a Kolmogorov law. So this third order structure function, which is velocity at two different points, difference, take the difference and take the component along L, so it should be L here, okay, L, and cube it. So this is a formula. This is proven to work for small viscosity, and epsilon is the energy cascade rate. So this is the formula. Now I apply the same prescription, velocity reversed. If I reverse the velocity, what happens to S3? So U is a odd function, okay? So this formula is odd function in U. So this is going to become negative, right? So if it is positive number, it will, so this negative number, so this is going to change sign. So I'll get, after this prescription, I'll get plus 4 by 5 epsilon r. Same U, but I just reversed it. Now in the reversed movie or reversed snapshot, what is the energy cascade? In fact, I can compute this flux from a given snapshot. I don't need a lot of, for entropy computation, we require many configurations. I can do it for single configuration. I can compute this flux, and this flux happens to be having negative sign for 3D. That means energy will flow from small scale to large scale, which is nonsense. So from this formula, which is structure function, give me a frame, I can differentiate that frame with a fake movie frame. Okay, so that can give me the arrow of time. So this energy flux is a good measure for defining arrow of time. It doesn't involve entropy, and it is a nice formula. Earthquake, yeah.
When you say space,
No, configuration, look at this velocity of this.
velocity.
Velocity, yes.
You know, if I show you a movie and I take a photograph, and
Yes.
it's still framed to that movie, I don't know the velocity. I know the velocity only by the
No, well, okay.
unless you've got arrows drawn on there.
Okay, velocity of nearby snaps, two frames, two frames. When I need velocity, I nearby, okay, nearby 2 frames. Okay, if you give me velocity, then I can do it. Yes. Now, earthquakes, astrophysical turbulence, crack propagation, human body also, I would say, the energy typically flows from large scale to small scale, like in cells. I eat my food, it goes to my stomach, and then it cascades. So in some sense, energy is flowing that way. And biological time, maybe this is one way to define. Now, let's look at, now this is, in fluid turbulence, we have viscosity. Now, somebody say, well, it's trivial because there's viscosity, there's dissipation, no problem. So it's already dissipative system, there's arrow of time. But we can also apply this to Euler turbulence, which is non-dissipative. Molecular dynamics, I'm going to just show you describe this in a minute. And quantum turbulence. Quantum turbulence has no dissipation. So this is a MD simulation done by my friend in IIT Jammu. So in fact, it's some kind of model of the atmosphere. So for each molecule, this is disconnected from heat bath. We make it isolated. So each molecule is given a random velocity as well as some spin. So we want to imitate a vortex in the atmosphere. So typical molecular dynamic simulations, we start with random motion. But you said, no, don't start with random motion. You give it some vortex motion as well. And let go. So you let go, then it starts from here, it becomes like that, then that. So 2000 kind of a time scale. Now, so this large scale order is getting disordered in this system. In fact, it's kind of similar to what happens in Euler flow. Okay, it's getting more and more disordered with time. Now, how do I explain this? So there's no viscosity in this, yes? If you are talking what you are talking earlier, that's the thermalization. Euler has dissipative. No, Euler has U squared for discrete is Euler. I mean, for Euler has U squared is constant. No, viscosity is 0, so No, integral u squared is a constant. In u squared dx is constant.
I think he's talking about these.
For the finite functions, it's finite, but that probably you wouldn't compute.
Why not? I mean, I think now that's another question which we discussed in the morning. So in nature, do we really get tiny? Well, there's a dissipation, there's a scale at which it cuts off. So here, I mean, this example or quantum turbulence, there's a scale at which cuts off and some other things take over. So I'm discussing physics aspect, okay? I'm not discussing the singularities of Euler. And at that cutoff level, the energy is conserved.
He's talking, I think, of these weak solutions.
Well,
Which are not continuous, I mean, which are not differentiable.
yeah, so mine is truncated Euler, if you may call it. Okay, so but truncated, so the pictures I showed you is truncated Euler, which will be close to reality. You know, reality, there is some truncation at some level. Quantum turbulence, there is definitely cutoff, which I'm gonna well.
I have a question, Mahendra. This is Mahesh joining from Japan.
Okay.
In your previous slide on the third order structure function, you said that you can compute the third order structure function from a single snapshot, which is, the statement is true. But in the inertial range of turbulence, where we assume that the viscosity is in the limit of zero, you can have redistribution of energy from small to large scales momentarily due to the violent fluctuations.
Right.
And so on occasion, you can see from instant to instant, sometimes the third order structure function can go positive. But if you take a time average over many snapshots, progressing over several large eddy turnover times, then
Right.
of course you will see the minus 4/5 epsilon r.
Right.
So the statement that it holds at every time instant is not it does not hold.
Yeah, I grant you that. So in fact, the epsilon r is going to be different numbers. Sometimes the real flow can show back scattered.
Yes.
But on the whole, it will most of the time
Yes.
it will be positive.
Yeah.
That
So it's
I
a
agree.
statistically average. Yeah, it's an average statement. Yeah.
Yes, it is average. Yes. Okay, so let's continue because I want to finish on time. So here, so origin of dissipation. So this is a isolated system. So origin of dissipation. So let's look at how do I get dissipation in the system. So in fact, that's how it is defined in statistical physics, Rice book. Okay, so we look at it here. The velocity field has two components. One is average velocity and one is fluctuation. Right, so I break in two parts. Yes.
Question. I'm just trying to understand. So you're saying here that you're trying to characterize the flow of time by looking at flow of energy across scales.
Yes.
But if I was to just do it by counting, the volumes in phase space of initial configurations and final configurations,
Okay.
can't we just look at flow of time by saying you start with a less likely configuration and you go to a more likely configuration? That's what we would usually have said, right? When you study thermalization, you start with an exponentially unlikely configuration, and then it goes into a more likely configuration. So what is the problem with just using that to discuss dissipation and the arrow of time? Why do we even need to discuss all of these other issues?
That depends on who are talking to. So I think there is a community in condensed matter physics which likes that, but there are people in molecular dynamics present this way. So in fact, we don't talk about configuration space. We talk about energy. We talk about real space and Fourier space. So this depends on how you look at it.
You could do it in Fourier space. I'm just trying to count the number of configurations that are consistent with some observations I make, whatever I'm observing, the velocity field. And then I try and ask, how does it go from a less likely configuration to a more likely configuration?
No, I agree, but this is an interesting viewpoint, but I have not looked at it. And most people don't look at it in this field. So you look at Fourier spectrum. Spectrum is like all the turbulence literature, they talk about spectrum and flux. That is what is used in the community. That's the picture which we are presenting. And hopefully, these two fields will find consistent picture. Okay, so that's my perspective. So you look at this one. Now, this gives a very nice way to get dissipation. That's what I want to show you. So typically, especially in 3D and some 2D systems, what happens to this part? So if I plug that in, I get total kinetic energy is kinetic energy of the mean, this VA hydrodynamic plus fluctuation. Okay, and the cross terms vanish because VA bar is nearly constant compared to VA fluctuation. Okay, now in this picture, this is going down. That means this is decreasing with time, but this is increasing with time. So this is the origin of dissipation. So I'm getting thermalized. So this is a conversion from coherent state, coherent motion to incoherent motion. So even though system is conservative, we can invoke dissipation by this mechanism. So classical systems like I have n-body simulation, if it is getting thermalized, so I'll say, well, nobody will say there is a dissipation, but we can say there is a dissipation by this mechanism. Now in quantum turbulence does show Kolmogorov spectrum plus other things. Now it's very surprising, no, that there is no viscosity in superfluid helium or BEC. There are a lot of very interesting experiments in BEC. It shows 5/3 spectrum. Why so? So it turns out there is energy conservation, there is momentum conservation and particle number conservation. So, but here there is a phonon coupling at very small scales, the compressive modes, and energy goes from incompressible modes to compressible modes, and that acts as a dissipation. And this is precisely what's happening here, or in both the systems. So conservative systems can show dissipation. That is what, in fact, I was impressed by this argument. And so we don't need to say friction is a dirty word. Normally say, well, friction can't be modeled, so we don't want to talk about it. Just keep to Hamilton systems. Friction is coming from here. Now, open systems, as I said, force was time independent when we said that time symmetry is respected. Yes.
Is that conservative or not? Everything in which a first law is conservative or not?
Actually, I'm just looking. So first law is converting from work to energy, work to thermal energy. So in some sense, yes, it is like this system where we had this gas which was pushed by piston, and we are pushing this the piston energy into thermal energy. So in that sense, that picture is consistent. Okay. So for open systems,
Sorry, Mahendra, one more point. In your previous slide about our previous remark about BEC and superfluid helium, where you mentioned the -5/3 spectrum, I want to just make two qualifiers. One is the -5/3 spectrum of Kolmogorov is not a statement of time reversal symmetry breaking. It's the third order structure function, because you can't use a symmetric function like the second order structure function to talk about time reversal. The -5/3 spectrum is a statement of the nested structure of the eddies or the cascade the structure at a particular snapshot in time. But in order to get the time reversal symmetry breaking, the breaking of detailed balance, you need a transport, you need a flux. So you need the epsilon, the -4/5 law, the third order structure function. So you need an odd function in time. The second point is we do come across -5/3 spectra in many systems in nature, but to ascribe Kolmogorov to them just because they have -5/3, it's not a commutative relationship there.
Okay, so for the first comment, third order structure function is not defined when we don't know how to derive it for quantum turbulence. It has to come from the equations are compressible, right? The velocity field.
Yes. Yes.
So I just meant to say there is a regime where they see 5/3 that is signaling positive cascade. That's what you mentioned. So I qualify it further that indeed there's a energy going from large scale to small scale in quantum turbulence. In fact, they are driven, and that energy is getting dissipated somewhere, and that is by phonons. That's what is
got it.
The community agrees. So we agree apart from semantics, which I kind of ignored at that point. And 5/3, okay, I mean, I need to, so I think the second part, let me just skip right now. Okay, so let me try to
Okay.
finish that part. Now, so here, if the forcing is time dependent, then timeless symmetry cannot be applied anymore. It is by definition, the solution will not be time symmetric. And nature, we find lots of such systems. Like turbulence is one such system where we force the large scale, right? So that is already breaking the time symmetry. Earth, it is driven by the sun, which is time dependent, forcing by the sun. Macroscopic world, we have a lot of systems which are driven by time-driven forcing, so no question of timeless symmetry. Also, chemical reactions like combustion. There is a huge explosion, or even if no explosion, there's energy, there's a sound coming out of the engine. So all that we can't push back. I think causality is a very strong principle. A causes B, and so B should occur after. Even in a relativistic way, law of karma, okay, that's something which I would say it catches up. And that is giving us a time order. Now, the asymmetric object, I'm reaching the end. Asymmetric objects, as I said, with rockets, we can clearly differentiate the forward motion versus movie played backward. No doubt about it. So we have spherical balls. Yes, we can't differentiate forward motion and backward motion, but asymmetric objects we can. So by the way, so through a rocket, the one example I said is if I play the movie backward, whether I can say that it is a fake one or not fake one. So yes, but that's not aerodynamic. That is not. So real life, real rocket throwing backward, we never see. Okay, I didn't invoke. Okay, so I stick. So for example, aerodynamically, no the air is always there in open world. Aerodynamically, the backward motion is not going to work. Okay. Yes, in the world things are driven, as I told already. It is driven. So
it's distinguishing between the geometric part versus the driven.
The geometric part too. So lot of chemical reactions. If it is asymmetric, it will be preferable than if it is not asymmetric.
Right, because the rocket is interacting with the air.
Yeah.
So the time reverse thing of this would be the molecules converging on the rocket and pushing it behind, which of course could happen, but it would be extremely unlikely. But this is just the example that if you take an open system, in general, it makes sense for the system to, if you just look at the Born rule, for the system to radiate outwards. And it's very unlikely for the environment to actually converge onto the system.
Yes, so I mean, all these are possibilities, including some shapes. Some shapes work better because they are asymmetric. The aeroplane is asymmetric, it works better. If you have symmetric wall as aeroplane, it won't work. And that is also giving us a direction, right?
Relating to the issue of the arrow of time, this is a
So I was just relating with the movie played backward. Movie played backward, can it differentiate forward motion with a forward movie with a backward movie? Backward movie is we can easily differentiate. So let's look at this movie. Okay, this is how asymmetry of objects can easily make it unreal. Okay, now the man is not symmetric. It's not a part. Now I am going to play the movie backward and say, well, this movie is fake, right? You can say that playing backward. So I'm not making any profound statement, but the statement is equally invalid. Microscopic world is symmetric, the laws are symmetric, so the whole world should be symmetric. I'm just saying that it doesn't work. So let's play the movie backward, okay? Now, by the way, the person talking, you can't differentiate, if he's talking really or not talking, but the person going back from the pond. Now, you don't, I mean, of course, you can look at the person's molecules. If I reverse it precisely, I'll get there. But I think it's meaningless. I mean, the world is not going to be, man is not just a bunch of molecules who I can reverse. Now, by the way, this one doesn't look like time reverse, but it is time reversed, okay? Now here it is walking back. By the way, which movie is it? Somebody knows? Diwali. So here you can see this is a person which is asymmetric, and we can easily see that it is fake movie, or it is thing moving backward, and this is what really happens. So saying that balls, symmetric balls are time reversal, it should happen for the real world. I'm saying no, that's not going to carry forward. Now these are the atomic collisions here. These are this spherical ball, but it just goes one direction. So bring them back. Now first of all, you have to be precisely bringing them back to come to the original configuration. It doesn't happen. Now the last slide. So time reversal operation. Now, so this operation, as I said, sometimes it's just bogus. You can't time reverse. Now, this person is breathing oxygen. Red is oxygen rich, goes in and breathes out carbon dioxide. Now I want to reverse it. So what's going to happen? So I'll be breathing in CO2 and breathing out oxygen. Look, what I'm trying to say is some of these assumptions are bogus. Okay, so we can't quite say, well, I can time reverse everything. Time reversing the universe. I mean, look, I can't time reverse the universe. It is not in my hand. So that's why my point is.
The universe, we might have a better chance, but
So if we can't do it,
just maybe the universe will spontaneously time reverse and so on. But the basic example you're giving is just that you throw a stone into the pond, and of course you can make out the reverse movie, which is the ripples converge on the stone and throw it out. But maybe I'm missing something. If you could please explain this, we would always explain by just saying there's an asymmetry in initial conditions. You had some initial conditions, and the initial conditions you started with were also fine-tuned. We just happened to be coarse-grained with respect to us as observers, so we felt it was natural. And the reverse initial conditions you need are also very fine-tuned, but it's hard for us as observers to arrange them. But is there any? I'm not understanding the point. Maybe there's something I'm missing about the point beyond that.
So first of all, if the world is symmetric in time, I should see the forward motion and backward motion equally likely. Yes, so that is part of the macroscopic phenomena, that initial conditions typically lead to the phenomena what we see. Okay, so I agree. Typically, so aging, so aging is coming from initial condition, and it goes that way. I can't, and one implicit part is that this time reversal operation, nobody time reverses my body, right? I mean, we can't, but precisely, so I agree with you. That's the reason why this statement that we can, why don't we grow younger, it originates, it's a puzzle.
Mahendra, I think the point is that that's like a straw man in some sense. I mean, no one is saying that, right?
No, by the way,
no one, I think, in the, who would be looking at it from the point of view of microscopic configuration space or phase space or availability of configurations, no one would seriously say that time reversal of some particular thing should be.
Look at the video of Coral, okay, and the green. So it says, why doesn't the broken glass come together?
Right.
If I reverse the velocity.
Should they also say the same reason that?
Yeah, so first of all, reversing the velocity of the broken glass is not possible. Secondly, even if you could reverse it, there are condensed matter phenomena like grain boundaries and so on, that will not make it work.
And in general, the world is irreversible because this light has streamed out, the light that's coming here, and
Yes.
it's gone, and we can never catch it. So unless someone is surrounding us and is going to help us, we can't reverse the world because there's decoherence happening all the time.
That's what I'm
But
saying.
this we all agree with. So there is no mystery in this fact that you
By the
start
way,
with initial conditions.
Look at, so, okay, great, but my paper was rejected 9 times, which I precisely said this. So so it does nothing wrong with the paper. But look at entropy. For example, entropy is not defined for many systems. We agree with that.
This has nothing to do with it.
So
I would define entropy using S maximization, and then I would say it is defined. And I would say
I disagree with that. So that is what, I mean, by the way,
it's a definition. It's just a definition.
No, but for hydrodynamic systems, I had difficulty in defining entropy. And I think, look at the literature for Euler systems, the entropy is not defined.
Yeah. So a stationary state of a driven system has the property that even in that stationary state, if you show a movie, you'll be able to tell a forward movie from a backward movie. A stationary state of a thermal equilibrium system, even if it's made of weird shaped molecules, they can be arrowheads, they can be squirrely, twisted, anything, you will not be able to tell the difference between a movie played one way and a movie played the other.
Sorry, Sriram. No, so, Sriram.
Yes.
I have spent years looking at videos of turbulent water.
Yes.
I played forward and backward. I can't tell which one is time forward
it's
and time
true
backward.
It's true that you might need to. Mahesh, just a second. Mahesh, just a second.
I have to do transformations on that to be able to do it. To be able to figure
True,
out
you
the time
might not be
reversal
able to tell naively. You might need to stick in clever probes to tell. In the case of a thermal equilibrium system, no probe will tell you.
Yes,
Oh,
agree.
by the way, for turbulence, I can use as flux. You'll find it.
Fine. I mean,
Flux is, that's why I'm saying it's
my point is made.
simple.
Anyway, look, I think I've said enough.
Okay. So anyway, so I should speak. Somebody,
Just a fun thing I wanted to add.
yeah.
This photo shows it has nothing to do with time. This photo shows that you can put off a candle by blowing, but you can't put off a candle by sucking.
But it has to do, well, I'm talking about time-reversal operation. Look, all the five symmetries, they're easy to perform. Translation, rotation, time translation. But this operation is a pretty tricky operation. That's what I want to say. And basing the assumption, whether I'm happy that we have converged, but there are talks attended in TED Talks. And these are statements made, why is the world time reversal asymmetric? Now, you look puzzled, Sriram. You can just look at my point is, in my Feynman lectures, last chapter on symmetries, this seems to be a puzzle. And that induced me to say, well, this is not a puzzle really. And I'm happy that you agree with that. So, time reversal operation, by the you agree that is a pretty tricky operation. But I disagree that whole universe can be time reversed. That's a joke. No, but people talk about it. Entropy of the universe is increasing. What does it mean?
In fact, one might ask this kind of a question, which I feel might be a different, maybe more subtle question, which is why did the universe start in a low entropy state? That's kind of a question one could ask. But then it would end up into questions of how do you define the set of observables and how do observers emerge in the universe?
I'm sorry to say, this again a pre-assumed stuff. Entropy of the atmosphere. The model which I showed you about the vortex and the particles, total entropy is not, it's sum of the entropy of the hydrodynamic, which I showed you, and Boltzmann. They are different. One is extensive, one is non-extensive. So defining entropy of the universe, I think, is senseless. Actually, you can't define entropy of the whole universe. Because there are objects of different non-equilibrium, what kind of entropy are you going to use?
The universe in terms of a fluid and a metric, and one could define an entropy within that description.
It's a non-equilibrium matter. If I can't define for the atmosphere, how can I define for the galaxy?
Well, it's a question of how many galaxies. The universe is very simple.
That's an assumption. I'm sorry to say, there's an assumption which we are using, which we can't. If you can't do it for atmosphere, how can you do it for galaxy?
I mean, it's the same reason we can sometimes understand large-scale systems because they simplify. We might not be able to understand.
But that is what simplification is not fair. That's what I'm wanting to say. In fluid dynamics, I worked on, and this just doesn't make sense. We need, so the slide I showed you, atmosphere, the entropy is not sum of hydrodynamic entropy and the Boltzmann entropy. We did try these as two, they have different properties, extensive and non-extensive. So they are connected with that. Entropy is connected with time, arrow of time. Well, I won't say independent, connected, but connected. Well, not independent, but let me just close it, okay? So this is the same slide we've already seen before. And this is my last statement, okay? So I think people seem to agree, but I thought, anyway, great. So I've convinced that arrow of time is simple problem, which is great. Thank you.
Can I make one couple of comments, Mahendra? So
yes,
one is, it's actually very difficult to define entropy for driven non-equilibrium systems like turbulence.
Great, I agree
as you
with
point
you.
out.
Totally.
The reason is if I were to evolve the phase space of a system like a tank of water into a turbulent state, it will go from phase points occupying being equally probable of occupying every point in the hypervolume of the phase space, they start clustering and start executing hydrodynamic flows of the compressible kind. And this is the work of Ruel and Sinai, because it follows what we call the SRB statistics, or the Sinai-Ruel-Bowen statistics.
Right.
And the phase space starts shrinking because there's dissipation, but it has a fractal shape. So if I cannot ascribe equal probability to every point in phase space, how do I define entropy? So there is a more fundamental mathematical problem to solve there.
Mahesh, I think we don't want to do it that way. For non-equivalent
I
systems,
agree.
why don't you use the formula which I gave? Use the spectrum, and you can do it for every snapshot and time evolve it.
Then it brings us back to the point I made. The spectrum does not tell us about it. It tells you about the fractal structure of the cascade. It says that the system you're looking at has a fractal or a multifractal structure. It doesn't tell you anything about the direction of the energy transfer. That has to come from an odd function in time or in space.
Yes, we are also trying. Yes, I agree with you. So there's a phase entropy, which is Kuromoto, who is winning the Nobel Boltzmann medal. Phase entropy is another measure which we are trying to do. But that is also pretty simple to define in terms of phases of these Fourier modes. So, I mean, I think it's not the only answer. I think one can do many more things from here.
The second is more of a suggestion. Please take it with a pinch of salt. You have full freedom to decide what you want to present. I felt the point the example you were trying to give of the shape asymmetry influencing time reversal symmetry breaking. The simplest example I can think of is the ratchet and pawl, because the gears are asymmetrically shaped, and if you had spheres which are symmetrically shaped coming and striking it, it will always move in one particular direction over the other direction. It's a much simpler system to envision time reversal symmetry breaking rather than a rocket. Because if you go to the case of a rocket, our good friend Elon Musk has shown he can land a rocket in reverse. So there's a problem there. Of course, there is a way to show how that would work too. This goes all the way back to Rankine. You can show that the power, the thrust goes as velocity squared, the power goes as velocity cubed, or speed cubed, whichever way you want to, and that is asymmetric.
I see.
And that is related to the cross-sectional area of your rocket. So the shape will not come in.
Okay.
So as a result,
I need to think more. I mean, I grant that part. So that was one of the things which I need to sharpen. So basically,
well, we'll chat when you're in Japan in September.
Yeah, I will. Yes. Look forward.
Thank you very much.
Thanks, Mahesh. Yes.
I have a comment about your last line. Of course, I agree in general that it can't be generalized. Although in this case, I think this issue of asymmetry between initial and final conditions is also visible for point particles and isolated systems. When we compute the cross-section, even in quantum field theory, we average over initial conditions and sum over final states that are consistent. And just that itself tells you there's, that because you're preparing the initial state and then you're averaging coarse graining over whatever you see. And that itself, I think, will help to understand is this issue of, why the phase space density of the final states, if it's larger, it enters because you prepare something. So in this case, at least, I think this lesson we can learn also by looking at point particles and isolated systems.
Okay. Yes. So I should, Yeah, I in fact, sensitivity to initial condition is possibly related to this phase space volume, which yes. Yes, I think that I believe that, in fact, I learned from Rajesh. That was my learning today. So that is connected, yes.
Any other questions, comments?
I'm not a physicist. So
neither am I. I'm a fluid dynamicist.
Math, I don't get it. But there's something that I was all the time thinking about, and it is, what's the definition of time that you are actually using in order, because all of these systems seems to be defined by using some sort of time, but at the same time, they feed back into being used to define an arrow of time, right? So there's some sort of like, so I was thinking in a way like a definition of time, which actually I really like, which was given me by Loganayam, which also is, no, it's a ball rolling on a plane. But then if you have that, then you can reverse very easily. But I think actually my head, generally, I think time is thought like that. So time reversing in terms of like a ball rolling on a plane, this is of course, even with the movie or everything, a classical example that work. So I was actually wondering if in the math, this is included. Like the definition of time in itself, because you can increase like discretely, 1, 2, 3, la, 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 or you can have a ball running on a plane, right? So
if the differential equation like Newton's law, Newton defined time in one way, Einstein kind of defined it further. So time is something which is, for me, is Newton's law, the time out there. And so the equation itself does not contrast forward or backward. Equation itself, if the force is symmetric in time. So initial condition is one such way. So we have 3 balls. If I just start randomly, they're sitting in a triangle and they start randomly, they will not remain on triangle. That is initial condition sensitivity. Or some kind of you let go and so typically it tries to become random in a Boltzmann gas. So let it be in the one side of the box, times reverse symmetric equation, but it becomes random with time because of, I think it is connected with evolution, randomization. It just initial condition plays a role. So we are not thinking philosophically about time. For me, I'm just practical, this fluid dynamics. Time is a parameter of the differential equation. And it doesn't give the arrow. Time does not give the arrow. That was a major point. Fundamental laws do not give the arrow. And in fact, my whole talk is that saying, well, there are other things which give the arrow, which are obvious. That's what I'm trying to say. Which is like open system interactions, the energy flowing from large scale to small scale. That is not part of the equation, but energy is fed in the system. Okay, I hope I'm getting something. Okay. Thank you.